So we will be very strict for this last session because we have also many young guys, so they can be very fast. So please, computational session now. So we change a bit the topic, and you are the first one.
Thanks a lot. So
from Berlin, I forgot to say.
Yes, because this section is leading to the banquet, so it's probably the most important section.
Yes.
And as you can see, I'm going to show you some computational stuff. Because of that, it's going to be not so boring. So I'm going to keep you active as much as possible. I'm working with the group of Wolfgang Müller from Berlin. I hope you can see it a little bit. It's a little bit small, but let me start. I know that many people have the same ideology here because I have seen also in the other talks, but let me start with an assertion. So I want to emphasize that if we say continuum, then we have a length scale. Everybody knows about the length scale. So if I have my specimen, my length scale is maybe 10 centimeter. But we have also something else. This is the lowest threshold. So the smaller than that threshold, we don't care, we don't detect. So let me give you a brief example. If you have aluminium and the lowest threshold is maybe 0.01 micrometer, and smaller than that we don't detect. What is smaller than that? Maybe atoms, molecules, I don't know, maybe some interactions. We all ignore that, and we start with the assertion of our continuum. The lowest scale is the lowest length scale that we can have is 0.01 micrometer, let's say. And in this smallest possible threshold, the first order continuum, the Cauchy continuum, is accurate. Okay, this is how I start. So if you say no, I don't think so, let us discuss that later in the banquet. But I'm starting with that, and why I'm starting with that assertion is going to be possible for you to realize in a couple of minutes. Actually, Francesco already said that, but I believe it was a little bit quick. Because of that, I'm going to spend a couple of minutes to repeat what he said. So you know the pantographic structure. This is a computer CAD model, but basically what you see here is nothing else than these beams and also these beams, and they are connected by using pivots. So the whole structure is roughly 200 millimeters. So from here until that, it's 20 centimeters, that big. That means every pivot here is something like a couple of millimeters. So if I want to use the first order theory, Cauchy continuum, then I need to spend lots of elements, and we have a couple of doctoral students to torture, and we say, all right, let's do that. And they put lots of mesh here. As you can see, my mesh size can be as low as the lowest threshold of my continuum, and then I can capture every single detail by using this mesh. Okay, that means here I'm using the first order theory and then make something which we have also 3D printed and made some measurements. The measurement, and this is the exactly equivalent to the measurement, the computational result, by using first order theory. And what you can see here is on the left hand side is clamped, and on the right hand side we just shearing by displacement controlled mechanism. So, and this is also the equivalent simulation, and there is no scale. So we are not changing the scale. This is one-to-one what we compute. It's not big, but it's large, like huge displacements that you can see here. And from this perspective, it is not possible to see, but there is something interesting happens. If we shear it normally, we would not expect out of plane displacement, but indeed here something happens in the experiments we see, and also we do this complicated meshing by using, I believe, 3 or 4 millions of degrees of freedom and computing everything used by Cauchy continuum. We see exactly the same stuff that we see in experiment. That means there is an out of plane displacement in front and in back. Okay, here is clamped and here is sheared. This is the before this deformation, and this is after deformation, and you see here out of plane displacement. We think, we don't know, but we think this is because of the structure. We have a structure there, because of that probably we have this stuff. So in order to make it a little bit more really accurate for everyone, from other perspective, from the side view, you again see the out of plane displacement, and this is like the 3D perspective of the same stuff. Until now, what I use is the normal good old first order theory. if we want to go to another continuum level, that means if we increase the lowest threshold and say my smallest length scale that I can detect is 5 millimeter, then I'm not gonna see any pivots. These pivots and beams and so are all I'm not detecting. So then I can homogenize, but in this continuum I want to capture exactly the same detail I am seeing here with the structure. Then I need to use another theory, which is the second order theory. Because so that means there is, for me at least from my perspective, there is no arguing between which theory is better or not. So this is just, we are changing the continuum, we are changing the level of the length scale that we are using. And this is going to be exactly my agenda. First I'm going to show you something which everybody knows here. And why I'm showing it? Because of the strategy. Since the strategy leads directly to a generalization, and the generalized mechanics will be in the end showing that we have seen the complicated mesh we can use by homogenization by using something like a Stranger gradient theory. Okay, let me start the variational formulation of the weak form. In classical mechanics, I know we are here Italian and French community, so everybody will be easily convinced about this strategy can be used. So I'm starting with a postulate. This is one postulate, that there is one Lagrangian density, a scalar, an invariant function, which is describing the system. Of course, this is a postulate, so we are not discussing it. And what is inside? It's a little bit small, but the first one is x. X is coordinates, but these coordinates are mathematical abstract coordinates. Later on, this will be space and time. Okay, because of that, I'm using Greek index here. This Greek index goes, or will be going from 1 to 4. It's going to be space and time. Then we have phi. Phi is primitive variable. Because we are going to do mechanics, the primitive variable will be the displacement. And there's the gradient. Gradient means with respect to all coordinates, and since the coordinates is going to be the space and time, it's going to be a derivative with respect to space and time. And as you can see here, there's only the first gradient. Because of that, it's a first order theory. So what else do we have? There is a, nomenclature that phi and the gradient of phi together are called state space. Right now I'm starting explaining what is action. Action is again a little bit in an axiomatic way. There is an action which is the integral of L over the whole space, and this space is a mathematical abstract space, going to be space and time. And because we have a first order theory, there is also the surface of the space which is one dimension less, because we have first order only one dimension less. So the second postulate that I'm using is this action is invariant with respect to the transformation in the state space. Invariant means that the variation of A action is equal 0. Equal 0 is a restriction. It won't be equal 0 if we have dissipative systems. That means equal 0 means we have a reversible system. Elastodynamics, what we are doing here. And now there's a prime and something without prime. This is the same functional form, but the arguments are phi or phi prime, and prime means the transformation. So of course you're going to ask, what is phi prime? Phi prime is the transformation. I'm showing you the transformation. Phi plus epsilon delta phi, and delta phi is an arbitrary function which we will be calling later on in FEM jargon test function. So this is an arbitrary function, and because of that this transformation is really general. So now I'm going to make a restriction first. That means epsilon is constant, such that I can immediately find out that the gradient, because epsilon is constant, gradient is exactly that one. And second of all, another restriction, epsilon is small. If I say epsilon is small, then we can use a Taylor expansion linear in epsilon, and then immediately find out what is L prime. So we need L prime, and the subtraction of L prime minus L is action, which is 0 according to the principle of least action. Analogously, I can find out the same for the surface. The small s is a really small s here. This means the surface work, if you like. And we have the principle of least action, where the Lagrangian minus the Lagrangian L minus L prime is that one. And here we have W prime minus W is that one. So in this whole strategy, we start with one postulate, which is the Lagrangian density exists, and use the first order theory and get the pretty well known formulation of variational formulation of principle of least action. So it's a little bit abstract. Of course, we want to make it useful. Because of that, I'm now going into the direction of we want to make a continuum body in a reference frame. That means these abstract coordinates are the real space coordinates and the time. So small x is time and space. That means the infinitesimal volume element of space and time is dv and dt. And all these gradients are gradients with respect to ordinary space and with respect to time. So I'm bringing everything in. So here we have a delta phi, which is the arbitrary, for the FEM jargon, test function depending on space and time. And we have here phi dot means nothing else than the d to dt of delta phi. But as you know, in FEM, we like to do that delta phi is changing in space but not in time. So I have a problem here. If I want to calculate that one, the time change of delta phi is always 0, because in FEM we just set what delta phi, the test function, is. It doesn't change in time. So I want to get rid of that, and I'm using integration by parts. The most important message here is I'm not using an integration by parts here, because this is allowed. The delta phi, the test functions, are changing in space. So it doesn't hurt me if I leave it here. So I'm not using integration part there. So what comes at the end is this formulation, and this formulation is that I'm going to use and compute and show you some examples. So in elasticity, phi, the primitive variable, is displacement. So that means whenever I see phi, I'm going to use the displacement u. And on top of that, of course, I need to find out the Lagrangian. And the Lagrangian is a model. I'm just using a model where everybody would say, yeah, we already know that it's working. Because it's working, it should be not bad. We have a kinetic energy here. We have a stored energy here. I need to define the stored energy. Can be linear, non-linear, doesn't matter. But the most important stuff is the kinetic energy has everything which depends on time, rate. That means rate of u is inside. And here I don't have anything with rates. So I may have strains, I may have gradients of u, but nothing with rate. And here's something which we call because of the gravity we have conservative forces here. And on the work, on the surface, we have a work which is the traction vector times the displacement. Okay, this is the whole setting. I don't need something more than that. I'm just going to put L here, and instead of phi, I'm going to write u and find out the equation that you can basically read in every documentation like Abacus or COMSOL or whatsoever. So that part may be a little bit unusual for you, the stored energy derived with respect to the gradient of u. So let me explain what it is. Because we are in Italy, I'm going to call it Piola stress. So if you're going to be in Paris, in Paris later on, I'm going to call it Bussinesque, right? So in German, we want to give a German name. We don't have one. We call it nominal stress. I don't care. So it's a stress, all right? So, but normally, if you want to understand what it is, we can say, all right, what is that? We can use the Castigliano's theorem. I believe everybody uses Castigliano's theorem. I don't know why. And if you want to see, it's a really simple mathematical stuff to put it in by using the deformation gradient and see this one is nothing else than the stress. But we never need that. Okay, I'm just showing you in order to make you comfortable that that part is nothing else than the material stress. That's it. But we never use it. We only need, what we need is the stored energy density. That's it. Because this will give us what it is normally called stress, but we never introduced that. Okay. And now the strategy that we have seen I'm going to use in order to generalize. This is all why we are here, right? We want to generalize the stuff. And the generalization starts at the beginning, where I'm saying the Lagrangian density is not anymore depending only on phi and the first gradient, but also on the second gradient. So that means this is a second order theory. So all the rest, the scheme remains the same. So we have again the coordinates. These coordinates are the mathematical abstract coordinates, that means space and time. Nothing else than if we have the second derivative, we will have second time derivative, we will have second space derivative, we will have first space and once more time derivative. And the action is also the same, but this time we can have, because it's a second order theory, not only one dimension less, because here we have the second derivative, we can also have 2 dimension less. Okay, so we have the volume, which is the whole space, 1 dimension less, and also 2 dimension less. If you think that this volume is the physical volume, this is the surface, this is the edge. This is why I have a S here for surface, a E is for edge. Okay? So again, the same stuff, I need to introduce the transformation of the state space. Since epsilon is constant, of course this immediately results out of epsilon is constant. I'm putting these prime ones into the L, and then L prime minus L after Taylor expansion and so on, give me this time this principle of free section. So is equals 0, by the way, but I mean FEM people are too lazy, they don't write if something is equal to 0. I'm not writing it anymore. So this is equal to 0. Okay. So now the same stuff, I introduce the continuum body. That means the mathematical abstract x coordinates are the physical coordinates and time. And then we will have delta phi dot, or d to the dt of delta phi, or even 2 times, and I want to get rid of that, so I introduce again integration by parts, even 2 times, and here there's 1 integration by parts, here 2 integration by parts, here again 1 integration by parts. Because of that, on the boundary I'm getting some extra terms. Okay, this is really general without any restriction. Now I want to make a restriction and say, let me do mechanics. That means the primitive variable is the displacement. And in order to make a comparison, I'm using the same Lagrangian. This is not the most general case. Of course, I can now say, look, I don't have only u, but I have also the gradient of u, so I can also introduce a kinetic energy, which is the rate of the gradient of u, but it's difficult to understand what it is. And I want to make a comparison, because of that I'm using exactly the same Lagrangian. The only change is in the stored energy. So the stored energy can have, alright, stored energy can have now also the second gradient. And this is the final formulation that I need. Okay, only the stored energy that I need to introduce, the rest comes out automatically. So how can we solve something like that? Of course not by using commercial programs, but we can use open source programs that don't cost anything, the first good part. And second of all, you can program whatever you want. So we have a weak formulation here, which is a little bit different than in any commercial program. We can easily program that in it. So for any computation, for any CAD, for any geometry, we use Salome, open source, and it's a really nice program. And for meshing, we use Netcan. Netcan mesh generator is already in Salome. That means we just use our mouse clicks in order to make it. And we code in Python. Python is nice to engineers. You don't have to care about the structure constructor. So you just write, and then Python is actually interpreting it nicely. We use all the open source packages from Phoenix project. Phoenix project has actually something in it which is useful, which is the symbolic derivation. So that means I write the stored energy and the derivation is done symbolically. I'm not really using anything for the derivation of that part or that part. I'm just defining what the stored energy is. It can be complicated, linear or non-linear, doesn't matter, and the visualization is in parallel. Everything is open source. So I want to show you the numerical implementation such that you really get the idea. What I'm doing is I'm defining a stored energy by using the summation convention. Phoenix knows summation convention. I'm just reusing the continuum mechanical notation that I'm used to. And as you can see, this is the green Lagrange strain, which is nonlinear. And also here you see the strain San Bernard, the easiest one, stored energy. And then the differentiation happens exactly on that part, which is symbolic. I'm just writing in, and everything is done symbolically. So in the end, what we are interested in is, can we do, instead of this complicated pantographic structure, by increasing the lowest threshold, a plate which is homogenized, but now introducing some more material parameters or some more structural parameters if you like, and have the same type of deformation. So for the linear case, the stored energy density has these ones. We already have seen there are some coupling ones. The coupling ones are 0 if we just say it's centrosymmetric or isotropic. And then we will have only 5 more structural parameters. We don't know what they are. But now we have a computational tool. That means we can try to find out or understand what they are doing. This is what we started to do. We started with the simplest case. This is a beam, 3-dimensional beam. We just model. And we think that it may have a structure in it such that these additional terms, C3 to C7, may be different than 0. So I'm concentrating on only one, C6 is set 0, then we have the normal classical Cauchy continuum, or C6 is not 0, then we have the straight gradient theory with one additional parameter. And the difference is here. If we set it 0, then it's the classical old school case, and if we say C6 is something else, then we see that it is bending a little bit less. And this is normally called a stiffening. Why is this happening? Where is the energy going? Normally in an experiment you see only that and you say, okay, the material is stiffening, but it's not possible. We are putting the same energy in it. So the energy is not going somewhere else, then it comes in an additional, that one is the additional torsion. So there's an additional torsion. It's not only bending, although we have the force which had to do actually the normal shear bending. There's an additional torsion because of this parameter. And if I increase this parameter, this additional torsion will be increased such that it goes a little bit more on the right hand side, and also it gets more stiffened. So normally what people are doing is they use different length scales. That means the beam is in 10 meters, 10 millimeters, and 10 micrometers. The beam is getting smaller. All ratios are the same. The force is adjusted to that. And then what we see is that with the same parameters, that it is changing, it is stiffening more and more if we just change the length scale. That means automatically, if we even have in the biggest length scale this parameter in it, it is not dominating anymore, and this converges to the classical Cauchy continuum. And the same parameter, we could identify that the same parameter is doing something else that we could see in the beginning by using the experiments as well, that there is a out of plane displacement here. It is not perfect. I mean, it is not matching perfectly. It may be still so the case that we have other parameters playing a role in it. So we don't know if it's the case because it's not perfect. I'm showing in 2 different pictures such that you cannot see it's not perfect. Okay? So what is the difference? You see qualitatively something is happening here, but actually if your eyes are really sharp, then you can see that one is a little bit more non-local than here. It is just a local change here, and this is as the classical case that we're going to be expecting, and here it is something else happening. So we don't know if only C6 is possible to model something like that, but at least it is showing the direction for us. So what we have is, we have a variational formulation as strategy, which is without lots of questioning and without lots of question marks, immediately go on to a generalized mechanics. And we have a computational tool such that we can play around and we can try to understand more, or let us convince that it is working. And everything is open source. I mean, please go to our website, download and use it. It doesn't cost anything, and if you really like it, so well, just cite us maybe, or tell us if you have any problems. And I guess that was a sign because my time has finished. Thanks a lot.
Thank you. Thank you very much. Yes,
yes, thank you much. Thank you very much for your presentation and for the offer of your open source code. My question is, how do you handle finite discontinuity problems usually faced in higher order continua?
Is this your question regarding between the finite elements?
Yeah.
Okay. Really good question. That's a tough question. So we asked the same question, and we just tried to put Lagrange multiplier, just a penalty parameter, and see if it's changing anything. It doesn't change anything. So you can use, of course, the penalty parameter in order to force a continuity, or the jump of stress in the normal direction is getting 0. You can force that, but the result is not changing. So why? I don't know, but I believe that if we have a stiff, if the Young's modulus is high enough, then it automatically regularizes.
But this would mean, if I interpret it right, that you're using a mixed formulation.
So what are the degrees of freedom of your finite element at the node? You have only the displacement, or you have some?
Only displacement.
Only
no,
the displacement?
Yeah, only displacement. Within the element we have, of course, C2, but because we have second gradient here.
Yes, so how do you know that?
So you mean that there is continuous first gradient between elements?
There is no discontinuity, but if you mean the jump of stress in the direction of
Jump of the gradient of displacement.
yeah,
Not continuous.
they don't have to be continuous. Yes, and you can make them continuous by introducing a penalty parameter and writing the gradient between on the boundaries of element times 1,000,000, such that they have to be continuous. And if you do that, or if you don't do that, the results are the same. For this case, for aluminium.
So, but your implementation has this opportunity, or?
We did both of them, and they are yes. I mean yes, it's easy. It's roughly 1.5 minutes.
One question here.
Okay.
Victor.
Emek, how you will fight against non-uniqueness for nonlinear problems? In your case, what do you think about non-uniqueness?
I am not starting with the non-deformed configuration and go directly to the deformed configuration. I'm changing the force step by step by going slowly, such that
Lengths.
yes, exactly. So that means my Newton-Raphson iteration is converging to the next possible solution, which is correct, because I'm just starting and making a little bit bigger and bigger and bigger.
It was not buckling, in fact, what you have shown. It was not buckling.
No, it's not buckling, but
amplified the displacement.
yes, but you will not find a solution if you just start to make this huge displacement at once. You will not find the solution. I mean, the question is right.
That you can lose some solutions.
Yes, it is possible. You're right.
There was one in a short one, huh?
Okay. Two short comments. The first, when you find the coupling between the torsion and the extension, yes? I think it's not a gradient effect, it's a classical effect, because you have the non-symmetric layout in your sheet, in your composite sheet. From the point of view of composite mechanics, it's a non-symmetric layout. So the coupling between torsion and extension, it is a classical effect of anisotropy. And the second, could you show the results for the beams, where you have considered bending of beams? Yes, so it is the Midland form too, or what is the type of gradient theory?
That one. So the D has all 5 parameters. So this is
Midland form 2 or Midland form 2 or Midland form 1 gradient elasticity theory.
which one is more general?
They are equivalent from general.
So this is the most general possibility.
It's a Midland theory, yes?
No, it's not a Midland theory. I mean, if you want to call it Midland theory, okay, but
It was published in first in Midland.
okay. If you call it Midland, then it's Midland. No.
Yes.
He said common. He's not asking.
We have shown recently we have shown that in this theory there is no thickness-related size effects for the beams. And bending it was shown by analytically by strong.
Yeah, but you use beams. We don't use beams. We have 3-dimensional structure. We don't have beams.
But we have.
It's not short question, so we have to stop.
No, it's
So I think you will have to discuss during the banquet. Okay, during the banquet perhaps. I think this will be interesting to discuss that, but we have to stop, unfortunately.
so sad.
Okay.